gosh, I'm live. Hi, everybody. Hello, welcome, welcome. Today is Friday, March 24th, 2023. I am live from the South Texas Astronomical Society S.T.A.R party. We've got guided sky watching, or sky tour that's about to happen. I'm going to see if I can mic up Victor, who runs the society. There's tours happening over here. Oh, that's it. So
may continue to utilize the telescopes. You will have them pointed on Venus and the moon. However,
Venus, the moon.
please look up.
And I think Victor's up there.
Of our key scientists, which is Resaca, as he will be guiding you through.
Okay, so I hope y'all enjoy it. This place is packed. This is a super cool event. Okay, so they have their own. Where's Victor?
Awesome. If you all want to make
This
your
place
way
is.
over here, we're going to be starting very soon with our tour of the night sky.
I hear.
Sky through here,
Ouch.
but we'll be starting along with
My hand's getting squashed. Just gonna make our way this way. I've got like a light up thingy. Victor. Hey.
Do me a favor. Hold
Yeah.
on really quick.
Sure.
Actually,
Yeah. Here,
light works out better.
can I put this on you? Or will you put this on yourself?
What is that?
It's a microphone.
Oh, yeah. Well, actually, you know what? Richard's going to be doing most of it.
Okay. Then, he's over there.
He'll be coming over here. Right?
Okay. Victor runs the S.T.A.R Society. Okay. I'll put it on him. Not that I guess the microphone's could be loud enough. Hi, everybody. Let me know where you're tuning in from. Okay. This is going to be the sky tour. I'm going to go over here. Kind of get in front of everybody.
Jessica.
Hello. Oh my gosh. Hi. You run. I cannot see in the dark. Hi. Oh my gosh.
How are you? I'm so sweaty. I'm so sorry. Stream hears you right now. They hear and embrace. How have you been?
Oh no, I missed you. I missed you too. I've got to run and put a microphone on the sky. Hi. Good to see you both. Oh, what a great place to run into one another. It's my first event inside the park. Talk.
low.
You know what? You might be able to hear him through that microphone.
Cool. All right. Can everybody hear me? Yep. Everybody in the back? Somebody really far away, tell me if you could hear me. Oh, cool. That's cool. All right. Phil, can I have my laser?
Laser
Thank you.
pointers. Okay, so I need to mic up whoever's going to be talking.
Cool. All right. Well, thank you all for being here. How many of you are here that this is your first time at astronomy at the park? Awesome. Pretty much everybody at the front. Everybody in the back is like, oh, I've already heard this. I don't want to hear it anymore. Well, thank you all for being here. Thank you for people who are coming back. Thank you for the people who have never been here before. How many of you, this is your first time at Resaca de la Palma State Park?
Me.
Cool, good amount. Well, it is a beautiful state park, and we are very happy that they let us use their park for this event. I'm going to introduce us real quick. My name is Victor de los Santos. I'm the director for the South Texas Astronomical Society. We are a 501c3 local nonprofit organization. Our mission, which we will hopefully be accomplishing tonight, is to ignite curiosity through space science education, outreach, and by providing pathways to STEM for the community. We are here working in partnership with the University of Texas Rio Grande Valley. They have a beautiful observatory over there. How many of you all have already gotten a chance to go see it? Cool. So some of you still haven't seen it, so you're in for a treat. It's a beautiful research facility. It is the largest optical telescope in the Rio Grande Valley. I'm pretty sure south of San Antonio, because there's a lot of nothing there, right? And so we work in partnership with the university to help do outreach and to help show off what really cool stuff they have. And they do a lot of really cool stuff in there. They do a lot of really cool astrophysics research, and they have some very talented people. One of those people is my good friend Richard over here. He is a board member for our organization, for STARS, and he is also, he's our chief scientist.
That's the one I want to make
He's a PhD student at UTRGV. He's one of the first, he's within the first class of PhD physics students at UTRGV. They just recently got that program, so he will be graduating sometime soon within the first class.
Woohoo!
And now you will get to hear from Richard and listen to him guide you through the night sky.
Thank you, Victor, and feel free. We're gonna talk about the night sky together tonight. So, for those of you who haven't been here before, I usually start with a bit of astronomical navigation. So, how do we orient ourselves in the night sky? How do we know what we're looking at? I was just naming a bunch of stars in the sky, but it's systematic, so we can learn the process of doing that. And well, there's kind of a first step that we need to do. One, we're in the northern hemisphere, so that's lucky for us because the what's up?
So I don't have to hold this?
No, it is. It's a.
Yeah, perfect.
Okay, so this is okay?
Yeah, if you want to move it, you can.
Okay.
Perfect.
Oh, that's okay. Getting patched up here. Okay, so if we're lost at sea, or we're lost in the middle of nowhere, and we don't have a compass, how do we find north?
Okay.
Does anybody know?
The North Star.
That's right, the North Star. That's very good, very smart. So how do we find the North Star? Does anybody know where to look?
Wait, she knows again.
Oh, so I heard the answer, but what do you know?
With the Big Dipper.
That's right, the Big Dipper, exactly. So the Big Dipper, it's actually technically not a constellation, it's part of a constellation called Ursa Major. And it's hard to see here, but I'm going to point to the front two stars of the Big Dipper. So Duba and Merak. And what they do is they form a line, and it's hard to see here because again the tree line and the clouds. But basically, this would form a line, and you would find the North Star by just forming a straight line from the two front stars of the Big Dipper.
So when you can't see the entire Big Dipper, these two stars that Richard mentioned are actually, so this is the pot from the Dipper, the pot part, and then the handle comes down over here. So the bottom of it will be somewhere over here behind the tree line, and then the pot over here, and then those two stars are the ones that Richard mentioned points to Polaris, the North Star.
Cool.
And that's lucky for us because that doesn't have to be that way. There doesn't have to be a star just happening to be there. In fact, it's not always there. Over 26,000 years, the North Star changes because the Earth wobbles like a top. It's called precession. So the North Star was not the North Star that we know it when the pyramids were being built, for instance. So that's how you find north. In the southern hemisphere, you have to be a little bit more creative and find different patterns and orient yourself with that. That's also the reason why navigation took a very long time to develop, because it's very easy to find the North Star in the north and find where your latitude is, but you don't know where your longitude is. So in the night sky, we also have a latitude and a longitude system. It's called right ascension and declination. Those are two terms that astronomers use to, if you have these two numbers and you know these two numbers, you can point to that spot in the sky. There's a single spot in the sky corresponding to those coordinates. So for local altitude, right, if you know where, let's say the North Star is here, I can't really, again, point to it, but this height from the horizon to the North Star is your local latitude, the angle, right? So for Brownsville, it's like 25 and some change, 25, 26 degrees latitude. That's about 26 degrees up into the sky. So what happens if I take a trip to the North Pole and I watch the North Star as I journey north? The North Star is going to get higher and higher and higher in the sky. The North Star at the North Pole is directly overhead. As I go to the equator, I see the North Star go further and further and further down until it gets to the horizon.
Really dark here.
So basically the North Star is a natural angle to tell where your local latitude is. How far away am I from the North Pole? The other coordinate is a little harder. It's time, because the sky, rises in the east. We have a rise in the east and set in the west. That's actually what defines our time. It's called sidereal time. And that's the thing that took the longest for navigation, right? Because when you're out at sea, if you don't have an accurate clock, you're going to lose track of the east-west motion of the sky, and you're going to lose track of time overall. So that's basically how you do it. But again, just to orient north, the north part of the sky, we come all the way down to the southern part of the sky. And this line that I'm creating roughly is called the meridian. It's the line that connects the north to the south. And the meridian is very important because it's basically whenever something passes the meridian, it's the highest in the sky and it's the best to observe. So things rise in the east, and as they move across the sky, they get higher and higher until they get to the meridian, and then they start to set again. So astronomical observers who want to look at a target, they're going to try to look at stuff as it passes in this general vicinity of the sky, in the southern part.
Can I take it?
Yeah.
Cool. All right, so we know where north is. So who can tell me where the sun, who can point to where the sun rose this morning? Yes, you have all the answers. That's where in the spacesuit. Yeah, that general direction, right? So we know that that's north, so that's east over there, and then this is west over here. So Richard mentioned that there's a line that goes from north to south called the meridian. There's another line, and that is the line that goes from east to west. That one changes a little bit more depending on the seasons. It rises and it's a little bit lower. But wherever the sun rose in the morning, it was in this general part of the sky. It rose from this part of the horizon. It traveled across the sky, and this is during the day. If you would have seen the sun come in this general direction, it would have passed that meridian that Richard mentioned, and then it starts to come down until it sets. And so we saw the sun set over here on this part of the sky. Now, what else is on this part of the sky that you might see?
The moon.
The moon. Do you think that's a coincidence? It's not. So it's not a coincidence. So how many of you have ever seen an image of the solar system or a model of the solar system where everything is on a plane? It's like on a disk, right? So everything kind of it orbit, and all the planets orbit around the sun on a disk. So that's very similar to what it actually looks like. So because of the center of gravity in the solar system and the sun, all the planets orbit along that same kind of disk. And so we see that. So as the day goes on, the Earth is rotating, right? So that's what's happening. It's not actually that the sun is moving really fast. It's that the Earth is rotating, and we're seeing the sun. We're seeing the sun rise and then get to the meridian and then eventually set. So when the sun sets, what comes out? What can we see after that? The moon. Yeah. Well, we can actually see the moon during the day too. Have you ever seen the moon during the day?
Yes.
Cool, right?
Ooh,
We
Julian.
can also see stars, and we can see
Welcome
planets
to the
and
Kirsh
everything. And what we
fam.
notice is that the moon and the planets, they are also on that line. So if you look right under the moon, how many of y'all got to see Venus before it got too low? Yeah, so did you notice that it was kind of right under the moon?
Yeah.
So again, that's not a coincidence. That's because that's the ecliptic that you're looking at. So during the day, again, we rotate, the Earth rotates, we see the sun rise and set, and then we could see the stars, and we see the planets like Venus. And if you actually, you can make a line. If you go to Venus and then you go up to the moon, and then you keep on going up.
That one.
Yeah, that's Mars.
Oh, look at that. Cool.
So that's
Did you hear all the
Mars.
wowing everybody did? All right, I gotta
And if
go.
you keep, sorry, I don't like feedback. And if you keep following that line, and it will make that ecliptic, and you can follow it all the
There
way
it
back
is.
down to the
Upper left.
horizon. And unfortunately, right now we can't see any of the other planets, but that is that same path that all the planets travel on.
Mars is in the upper left.
I think Saturn is a little bit too close to the sun, Jupiter as well, so
That's so
we're not
cool.
able to see them anymore. But as they were in the sky during the day when the sun was out, we just couldn't see it, and they were along that line. And so in the morning, if you wake up really early, you're going to see planets start to rise, and then eventually, what else is going to come following it? Yeah, the sun, and then we won't be able to see any of them. Do you have a question? Did you have a question? No? Okay, cool.
See what
I think there was a question here, actually.
Did you have a question here?
Over here, to the right, to your right.
Oh,
Yes.
there's a satellite moving. Do you see that satellite moving, everybody? See
Richard,
it?
you want to take that one?
She asked you. No, I could answer if you want, but
So, do you notice how you can see stars up here, but you can't really see stars over here? Can
Yeah.
you guess why?
No. Moonlight. Oh, light.
Yeah,
Light pollution.
Exactly. Somebody said light. Somebody said light. So there's light pollution. So who can tell? Who's from Brownsville? Woo. McAllen in the house? No? Ooh. Hey.
People drove
Philadelphia, anybody? No.
So,
Indiana.
Philadelphia. Richard came all the way from Pennsylvania to do research here. Isn't that awesome?
Woo!
Yeah, we do cool stuff here. All right, so over here is Brownsville. So to answer your question, Brownsville is it's been developing over a lot over the past few years, and so that's really good, right, for us, but also really bad for astronomy. It causes something called light pollution. And so the reason that you can't really see any stars over here, and actually some of it, now that I'm looking again, it might be some of the clouds, but the light that's coming out over here is also blocking out a lot of the sunlight. So if you were in a really dark area, like have you ever been to like New Mexico or Arizona or somewhere where it's
Hey,
really,
Space
really
Girl
dark?
Falcon. Yes. Arizona skies are so dark. Hey, channel members, welcome. We've got Michael Maxey, Uncle Yukon, Space Girl Falcon.
Yeah, how many of you have
Nick
seen
Level.
the Milky Way?
Me.
It's really awesome, right? Well, I think the closest
Richard
place you can see it here, I always tell
Stan's
people
right.
go to the South Padre Island and go to the very north part of the island. That's
Hi,
probably the
Deslatino, I
darkest,
see you there.
spot that's nearest to here.
Hello, hello.
But unfortunately, we
Moonbeam
have some light
Bruce.
pollution here, and so to answer your
Spinnaker.
question, the reason we cannot
These are my
see
channel members. Thank you so
stars
much
during
for
the day is
supporting the
because
stream.
sun
Julian,
is
welcome Julian to the
brightest thing in the
Kirsh
sky.
Fam
It's extremely
team.
bright, a lot brighter than Brownsville.
Sirocco
and
Lopez,
it's blocking
hey.
out all of the
This
stars,
is-
at night, but they are there. The
This is
stars
at,
don't just
Resaca de
appear
la
at night.
Palma
They are there during the day,
State
even when the
Park.
sun is there. It's just
very
that
dark
it's
up
so
here.
bright that it's blocking out the light from the stars.
There's probably over 100 people, well over 100 people
Any
here,
other
maybe
questions?
200.
Sure.
So people
Okay.
this direction.
Oh, yep.
I'm right here.
There's gonna be like a mission to Mars or something. So like, when are they exactly gonna take the
Well, that's a good question. Usually with rockets, there's a lot of delays because of unforeseen things. But also they're developing the missions right now. So I think the estimate, depending on, I think Artemis 3 is supposed to be 2025, I think, or something like that. That could change, but basically the first human mission to the moon is supposed to be in the late 2020s. And I think Mars is sometime in 2030s at this point. But it could be in the late 2020s. It depends on how things progress, really. I don't know, do you have something, you want to say something about that?
Well,
What's up, Kenny Ray Horton?
so you said missions. So yeah, it's going to be a little while longer for humans to actually go to Mars, but there have actually been a lot of different missions to Mars already, just without humans. But did you know that Mars is the only planet that's purely populated by robots?
Ah, fascinating.
Yeah. So there have been a
Robots.
total of more than 40 different missions to Mars, and that's a large number. That includes NASA missions, missions from other agencies like the Japanese Space Agency and the European Space Agency. Also failed missions. It's not easy getting to Mars, so a lot of people have tried and then just they blow up in the atmosphere or something catastrophic happens.
There's a
But
satellite.
we have done a lot of different missions
There's
to
a satellite
Mars,
passing over.
and just so you can see it while I'm talking about it, because Mars is more fun to look at than I am. That's Mars.
Oops.
Is that the space station?
Space station? Yeah, cool. It's moving really fast.
There is another
Woohoo!
Yeah, it could just be a satellite.
It is a satellite.
It's going really fast.
So-
Probably can't see it. I'm back on two
So
legs on my
let's continue on the I see another hand. Would you like to answer a question? Sure.
How do you figure out the time change? Is it based on like the planets or stars?
That's a good question. So traditionally, what there's a couple of ways to do it. The moon is not a good clock, it turns out, because it's highly irregular enough to be a clock at least. You could follow the stars. So you basically define the stellar year, the sidereal year, by you pick a point in time. So in this case, it would be the spring equinox, the March equinox. You pick a point on the sky. Where is that star now? You wait until that star comes back to that exact spot a year later, and that defines your year. It turns out that that's actually still not precise enough because the Earth wobbles and it tilts and it's being tugged by the moon and all these other effects. So astronomers nowadays, what they do is they define a reference point around the sun. It's called heliocentric time,
it's not
and that's
the
because it's a lot more
ISS, okay.
stable. So
I'm not gonna
basically,
correct
if you were standing on the sun, which I don't recommend doing, and you do the same procedure, you wait until the stars come back again that year. That's a very precise year, it turns out. So that's how we do it. So please feel free to keep asking questions. I'm going to just continue with a little bit of star torch stuff. Piggybacking off of the ecliptic, I'm going to follow the ecliptic and we're going to look at some stuff here. So one thing that we didn't mention was that there is another planet by the moon, which you can't really see now anymore. Uranus is right below the moon. And actually, Venus and Uranus right now are both conjuncting the moon. It's called a conjunction. So some of you might have remembered the Great Conjunction where Jupiter and Saturn were together on the sky. Looks very similar to this, but of course, Venus and the moon are a lot farther away than Jupiter and Saturn were. If you keep going up, you have Taurus and the Eye of the Bull right here, which is Aldebaran. Oh, there's another satellite coming across.
Loud just got more loud.
How do we know that's not the same satellite that just came around the Earth again? No, I'm just kidding. That's true. It's dimmer, so it's likely farther away. But okay, so if we keep going, this is the Eye of the Bull, Aldebaran.
Oh, look at that.
And we have Orion, the Hunter. Orion's pretty much the most dominant constellation in the sky, at least for majority of the year. We're starting to get into late Orion season, so in the summertime, Orion at this time, tomorrow will be a little bit over here, the next day a little bit over here at the same time. So by the summertime, Orion's gone. But you have the Shoulder, Betelgeuse, very famous, Bellatrix, Saiph, and Rigel. And then you have the belts here. All of these belt stars are double stars. Betelgeuse and Rigel are variable stars. They change brightness, and they change brightness quite a bit, actually. You have the Sword of Orion right here. And if you look, the center star, what you have to do is you look at where it is and then use your peripheral vision. You'll see that it looks a little cloudy, a little milky, a little nebulous. That's because it's not a star. What?
What's a double star? You have a question.
What's a double star? Well, most stars in the universe are binary stars, so they have there's two orbiting each other, and there might be planets orbiting those. A double star looks like there's two stars next to each other, but they're so far away, it's just they happen to be in alignment with each other. All the stars in the sky, except the very nearest ones, if they have a true partner, gravitational partner, we would not be able to distinguish the two from our perspective. So the fact that like these stars, for instance, have companions near them, they're called double stars, not binary stars, because they look double, but it's just a perspective issue. One of them might be 100 light years further away than the other one, so it's just a perspective thing. That's a good question. And at the head here, it's hard to see, but you have the Pleiades, the seven sisters. It's not seven, it's actually hundreds. There's probably like a few hundred, close to 1,000 stars. That's the Hyades.
You can see the satellite, yay!
So, what's that?
Then why is it called the Seven Sisters?
So, yeah, the Pleiades is above the head. Sorry, I'm not even able to really see it. I guess it is this one right here. No.
It's a cloud next to the Pleiades. It's called the Seven Sisters because with the naked eye you can actually see about 7 stars in one little tiny spot. But actually, if you get a telescope and look, it's actually hundreds or I think thousands of stars. That's right. In one spot, and that's called a cluster. It's called a star cluster.
Yeah, and this Orion Nebula right here, this is like the youngest type of cluster. So this is a stellar nursery. If you zoom in with a telescope, you see a cocoon of gas and dust, and you see these young stars inside them being born and then migrating out, right? So they're actually migrating out. That's what our sun came from. And up here, the Pleiades is known as an open cluster. It's a young... no, that's the Hyades. Yes, the Pleiades is above... or did I have them flipped? Maybe I have them flipped. Well, Hyades and Pleiades are both the same thing. They're both called open clusters. Basically, they're a little bit more advanced in years. They're kind of adolescent stars that all the dust has disappeared, but they're still kind of all near each other. So hundreds of stars in there.
So Aldebaran, this is Taurus, the constellation of Taurus, the bull, and so you can't really see it, but it makes a set of horns right here. Aldebaran is the brightest star in the constellation, and Aldebaran is actually an Arabic word for follower, and the reason is because, like we said, the sky goes from east to west, so if you keep your eye on here, it's going to continue, not fast enough for you to see probably, but it'll
back there, it's behind the trees.
Here. And the Pleiades is about right here, so it's the story is that
Ursa Minor is down
Aldebaran
there.
is following the seven sisters, the Pleiades.
Those two stars right there is front of Ursa Major.
This whole this whole part of the sky is actually, it tells a really cool story. This is my favorite part of the sky because you have Orion the Hunter here, right? So like we said, there's Orion's Belt, there's Betelgeuse and Rigel and Safe, and so this makes up Orion the Hunter. Orion the Hunter is in the middle of a fight with Taurus the Bull, and so he's there fighting with Taurus the Bull, but he's not fighting alone. He has 2 hunter dogs with him, and so the dogs are right behind him, and they're
holding the
Canis
tripod
Major and
back on
Canis
the time,
Minor,
like-
which I think is above.
It's right here.
Yeah,
So
farther up here.
that's Sirius, and then up here is Procyon. So there's 2 stars here. That's Canis Major, as he said, his hunting dog, and then the other one up here, Procyon. And actually in the middle here, now unfortunately it's clouded over, Monoceros, which is another Greek mythological monster, is actually now hunting him. So he's being hunted, he's got help, and he's hunting this bull over here, Taurus. Now I can't really point to other stuff over here, but you have Leo, which is somewhere over here, and I believe one of these stars I think is Regulus. And then you have Gemini, which is directly above,
I'm a Gemini.
which we also can't see, and that's Pollux and Castor, the
Darn it,
twins.
can't see it.
So a lot of mythology stories here.
So quick fun fact, how many of you all like Harry Potter? A lot of people, right? So J.K. Rowling is actually a really big astronomy fan. So you might have heard as Richard was going through the stars, this star is named Bellatrix, and so Bellatrix Lestrange is actually named after that one. This one is Sirius, which also, by the way, is the brightest star in the night sky. And that's Sirius, like Sirius Black. And what did Sirius turn into?
Yep. Yeah, that looks
A dog, right? Like the hunter dog, Sirius. Yeah.
Venus. Oh, I'm down here.
All right.
I think that's pretty much the only thing we can see.
Are there any questions?
Yeah, questions and
Yes, one over there. Yeah, do you want to come up?
Where do you get the names?
Oh, good question.
Names are a very interesting topic in astronomy. Most of the star names are either Greek or Arabic. There's also a Latin name system. So typically the brightest star is called Alpha, and then whatever constellation it is. So if it's Orion, it would be Alpha Orionis, then Beta Orionis. And the brightest stars also have a proper name. So Betelgeuse, for instance, might also be one of those stars as well. So that's like the main way you would name stars, but then it gets complicated because there's planets have its own naming system, asteroids, comets, variable stars, galaxies. So depending on the object, you can basically ask specifically, okay, how do you name spiral galaxies? Well, there's the system for that. There's also a system for black holes. The black holes we know, they have special names. So depending on the object, we have a different type of way of naming them. But the stars are basically Latin, Greek, and Arabic based on history. So, yeah. Good question. Very good question.
Very good question.
Yeah, all the planets are actually named after old mythological Greek and Roman gods.
And the dwarf planets are named after underworld gods.
Was there any water on the dwarf planet? Was there any water on the dwarf planet?
Yes, so there's water found in pretty much every planet. Mercury has frozen water in its craters, even though it's the closest planet to the sun. Most asteroids have some sort of frozen type of volatile, essentially, but really comets and dwarf planets have the most because they formed far away, outside of the sun's influence, right? So that's why the rocky planets are close by and the gas planets are farther away, because the sun dominated the dynamics in the early formation of the solar system, consumed all the gas in the center, and
All the
left just
sunflowers.
kind of heavy metals. The comets, which come from outside of the outer solar system, contain most of the water ice, and that's where you find dwarf planets, so Pluto being one of them. The atmosphere of Pluto is only a few centimeters off the ground because it's frozen methane. So it has an atmosphere, but you would be standing on slush essentially for most of the year. So there's a lot of water on the outer planets, yes. Also a good question.
All right, if you have any more questions, we're gonna ask that you save them for later, but you will get a chance later. So we're gonna end the night sky tour here. I just want to mention a couple things. One, if you have children, If you're interested in STEM activities, we have some hands-on activities inside the visitor center. You walk in, you go to the left, and there's a room where they're doing some fun activities. Over here in the back, there should be two Dobsonian telescopes that I'm not sure exactly what they're looking at. One of them should be pointing at the Orion Nebula, and they'll be looking at things here. If you haven't gotten a chance to see that. In the observatory, tours are still going on, so if you haven't gotten a chance to go in there, go ahead and go in there and see what's going on there. There should be some of the other astrophysicists talking about how the telescope works and what's going on in there. Cool. And then last thing, in about 30 minutes, we're going to give Richard a little break. In about 30 minutes, he's going to be back over there in the pavilion area where the large TV is, and he's going to do a presentation on, what's it on?
It's going to be on solar storms and the fate of our star, but also an open discussion on all your astrophysical questions.
He's going to talk about really cool stuff about our sun, solar storms, and the fate of our star, where our sun is going. And then yeah, we're going to have some fun discussion. If you have any more questions, save them, and
see that one right there.
Cool. It does not have to be about anything that we're talking about.
This one, see Sirius?
If you have any other questions in space or astronomy or astrophysics,
and then Procyon. That's this one right here.
Thank you.
They're setting their setup. Thank you. Woo woo. Setting up right there.
I'm dropping all my stuff. Of course. I have a red light too.
Everybody has like their own little setups here. Over here, they've got a setup. They've got a setup over there. How cool is this? They'll just come and hang and do their thing, and
Me and my sister.
this is fun.
Wannabe astronaut.
He's not a wannabe. He's going to be.
All right, let me try.
I'm gonna put this down.
He's still mic'd. Let me grab him.
I'm just putting this here, by the way.
Richard. Sorry.
I forgot.
Okay. I was like, you're still mic'd. Thank you. Great tour. All right. That was good. All right. I want to go to the observatory. Observatory tour. Okay, it's possible I may have to like go away and come back. If I go away, I'll come back, okay?
If we were on another planet, it would just look like another star. And a lot of pictures happen.
It's possible.
My favorite image is my favorite picture. Have you ever heard of the Pelton dot?
Oh yeah,
There's an image called the Pelton dot. If you haven't seen it,
let's talk about Carl Sagan.
So Carl Sagan.
There's so many people here having fun. All right, that's really cool to see all the humans. I wanted to just give you all kind of an idea of what it's like here. This is a really well-organized event. You probably can't see. Oh, yeah. There's a lot of people here. There we go. All right. I don't know where the observatory is, but I definitely want to go to it. I guess we can go ask the people. We'll go over and talk, listen to this guy.
If you were trying to bench press or you were trying to lift some large equipment, you need to come. When it comes to the summer, we'll see some very high altitude Jupiter and Saturn. Easy to see, and it'll be. Did you take a look? Yeah. Awesome. Here we go.
Oh,
Let
that's
me
so cool.
readjust.
We are of course chasing I know. Come on, take a look. Yeah. Go down the road. And it looks like
Oh, they're checking out SpaceX. Oh, I knew him.
Oh my goodness. It's coming back. Take a look. It's coming back. Oh, go ahead.
Can I go in the way? Okay.
Yeah, you're good.
Thank you.
There you go.
Thank you.
No problem.
Awesome.
Okay, I want to mic him up because I know him. I wonder if he'll let me do that.
Oh, wait till I tell my spooky, my ghost stories. Here,
Oops.
can I help you?
Mercury.
Yep, that's it. You can still scare them. Open wide.
Yeah, it's beautiful, right?
Yeah. I'd hope you could see them. Hold on, wait. You see any aliens now? We're trying our hardest. We're going to try and get everyone here to see the moon before it disappears. We have a few more. This one is pointed towards Mars, but I'm going to...
Any question for Seth?
I have a question.
So, the persons are next up. I'm going to start to move out and then aim the Orion Nebula. That's a lot easier.
You're going to hit the nebula?
Yeah, so we're going to transition.
Yeah, sounds great, man.
To deep
Can I put
goodness.
Can I put a mic on you?
Yes.
Yeah. Okay. Camera's right there.
Yeah.
Not that you have to point at it. All right. Thank you so much. Your tours are so good.
Thank you. Okay, let's talk about Mars, guys.
Yeah. Mars. Let's talk about Mars.
Hi there. Yeah. Here, let me adjust it really quick.
All right.
Yeah, we're going to need to use this telescope to a better vantage point.
If I'm in your way, let me know. My light's blocking you, let me know.
Okay.
Oh, I actually have...
What we're looking at
a
in
mic
this
on.
telescope is
Okay, everybody, I'm micing up both people.
Okay.
Now,
Sounds good.
what
My name is Phil
planet
Dennis.
number is Mars
Awesome.
in the order of the
No
solar
problem.
system?
All right, everyone. So we're
I
going to
see a
look.
4 over
That's
there. We
okay.
got a
We're going
winning
to take a
number.
look right over here. We're going to move
so let's
this
see.
to
So
a better
if we have the
vantage point
sun,
because we're actually
we have
running out of
Mercury,
moon at the current moment.
Venus,
So you can take a look
Earth,
here. So
and then Mars.
what we're looking at is our moon.
So
who knows what the moon is made of?
We all know that Mars is red, right?
Okay,
Why
let's
is
be more
Mars
specific.
Red.
Moon rock. Okay, more
Very
specific.
close.
You'd be
Please, come take a
surprised,
look.
but when we went to the moon, and yes, we did. Don't tell me we didn't.
No,
when we went to the moon,
please wonder
we
and
took
guess.
a few pounds of rock back to us because we wanted to figure out what the moon was made of. We wanted to figure out if the moon existed in our solar system before the Earth or after the Earth or whatever.
In the rain for a while.
When we brought back all of that information, we realized that the moon
So
has the
Mars,
same consistencies
much like
of Earth minerals
Earth is
as
made
what
of
is here on the
iron
ground.
with some mud
So
caked
the
on the top.
nitrogen, the carbon,
Yeah.
the sediment, the iron.
Mars is a giant
Our Earth
rust
is
planet.
just as much as
It's a bit smaller
as
than
much
Earth,
as our moon is
but
a part
its
of
gravity is really quite good.
So when we look at our
It's
moon,
about
we're seeing
3/8
a reflection of our own selves
or
in a majestic
a better
way.
way to think about that
All right.
is if you were trying to lift
So
something
I'm
heavy
going to
on
move
Mars,
this. What's very,
you'd be
very
about
difficult to
twice
see right
as
now.
strong.
What we are going to do is we are going to move
so,
our line into an
iron-
easier vantage point.
Iron is really
We're going to go across.
oxidizing on the
Okay,
surface
so
of
everyone
Mars,
feel
and
free to
that's why
follow
it's
me
red.
as we go ahead and find the
what would
easier
it
vantage
look
point
like
to spot the moon.
if,
Okay.
if all of us here were taking a step out
Follow the
and
leader.
looking at Mars, stepping off of a spaceship?
Go ahead.
I'm going to do one at a
If
time.
it was,
Yeah, it's too much.
what was that?
Thank you very much. I figured it would
all
be.
of us were on a spaceship and we were taking a step out onto Mars, what would we see? We would see like red, like rusty, dusty kind of terrain. We would also see mountains in the horizon. It would be a lot like being in Arizona. Yeah, or southern Utah. But one thing that's especially interesting is the sunset on Mars. Our sunsets are these beautiful reds and yellows and pinks, but the color of the sunset on Mars is blue. Why is that?
That's cool.
That's exactly right. That's exactly right. The atmosphere absorbs all of the other frequencies, and the blues are what's getting through. It's a similar reason to why our daylight skies are blue. It's not actually a reflection of the
We're not.
oceans.
We don't need.
So if you're just walking up, we're pointed out right now. I might need to adjust it. Is Mars?
I might be in the way. Let's see.
We'll need to adjust it. I think the last two people have seen nothing.
Oh.
Alrighty. All right. Does anybody have any fun facts about Mars or have any questions? We are, as part of the S.T.A.R Society, we are here to try to inform and try to share anything that we can. So if you have any curiosities, that's literally why we're here volunteering our time. And if you don't know, if you've just arrived, we also have the Observatory where you can also look through that telescope. And we'll be having a talk under the pavilion about 9:30. Okay, it's 9:30 now. Probably in the next half hour, there'll be a talk by our chief scientist, Richard Camuccio.
Cool.
Follow the red lights, and you can't miss it.
Follow the red.
Yes. It's at the very end of the red lights. And if you guys want to go into the observatory, you are very welcome to. It's open to the public. Hey, there we go. Ooh. All right.
Cool.
Now you'll see a bright red dot in the center of the telescope. That bright red dot, if you're just walking up, is the planet Mars.
I want to see.
Mars habit. You got to adjust your eye.
Well, if we were to step out on Mars right now, we would need a jacket. It's very, very cold, but it's not that cold. So if you think of the old story that we knew as kids, where the porridge was too hot, Venus and Mercury, the porridge is way too hot. Mars, it's a bit cold, but Earth is just right. But how cold is Mars? Mars is actually not that bad. It's a bit like. Was that?
I think it's like negative.
During summer times, the temperature will get up to about 70 degrees Fahrenheit.
Oh, really?
So about what we're used to by temperature. But during their winter times, it gets down to about the temperature of Antarctica. So stuff that we definitely can manage. Let me know if you can't see it. I'll readjust it. Just make sure you don't touch the telescope. This one, probably 1,000 or so. But you could, if you want to inspire, let your kids have curiosity to it, you can buy a little kit telescope for just $100 or less, and you can start looking at stuff just like this.
That's cool.
Will it still be visible if it's cloud? You see the little dot?
It'll be harder to see. Yeah, I think the clouds might have gone over Mars at this point.
Is that the dot? I don't know if I
Yeah. No, let me take a look here, guys.
Bye.
Yep, that's it. Yep. Yeah, we can see through the clouds just barely. There we go. Yep. So if you take a look, you should see a tiny red dot there.
You see the dot?
Now, this telescope has a small lens. This is a 10-inch Dobsonian telescope. If you have a much larger lens, then you can see much, much more detail. Who remembers when the James Webb Space Telescope was launched?
I do.
Heck yeah. So that telescope has panels that fold out like an origami piece, and that is about, I think it's 7-meter diameter. Which means it's about the distance from here to that tree size of a telescope, and it has different instruments to study different wavelengths of light that we can't see with a glass telescope like this. So that little red dot is the 4th planet from the sun, Mars. I'm gonna set my bottle in.
Yeah.
Remember, it moves around.
No.
Oh yeah, let me take a look. You're probably right. You just brought up a really excellent point, which is that the sun is relatively fixed. Technically, the sun is flying through the galaxy. Our solar system is flying through the galaxy. But the planets, just as the sun is moving, the planets are moving around it. So if we're trying to track where the objects in the solar system and galaxy are, they're constantly moving. So we constantly have to readjust and re-find it in the telescope. The telescope in the observatory that you guys can walk inside of and take a look at, that, however, has a computer that will continuously track. If you don't know, the university here locally actually does black hole astronomy with this very telescope. And if you're curious, ask them about it. There are a few astrophysicists that are making presentations today. They would love to talk about it. Cool. All right. That is... Take a look. That little dot, that red little dot is Mars.
My future home, hopefully.
Now, who here knows why Mars is red?
It has dust.
It does have dust. Now, what kind of dust? If we leave a piece of metal out in the rain and out in the sun for a while, what happens to the metal? Yeah, exactly.
It has a lot of minerals.
Yes, absolutely.
Like, have you ever been in Alabama?
Yeah, very similar.
So the earth is red.
Yeah, it's,
Because it has a lot of
it has specifically iron.
Okay.
Yeah.
Wait, can you see it in the telescope when it's
Let me take a look and see.
Oops. Hold on, we're going to spin around, everybody. Spinning around.
So there will be one...
I don't really see it. Is it a dot? It's like...
Yep, that's it.
So it's literally moving right now.
So we know... Yeah. Like, okay, so think of this for a second. Right now, we're on Earth. But Earth is rotating.
We don't even know.
And we have the sun. And so Earth is rotating on its own axis. But it is also orbiting the sun. And just as much, the sun is flying through the galaxy. And so we're really like corkscrewing through the galaxy. And so we often say it's your birthday, right? What is a birthday? But a completion of an orbit. I call them orbit days to my friends. Yeah.
Another revolution around the sun.
Is it ready?
Yeah, please take a look. Yeah, this is Mars. It is my second favorite planet next to Earth.
You were saying that
Yes.
because it has a lot of iron?
Yeah, it's a rusty, dusty, the red of the planet is iron oxide. Yeah, so just iron is oxidized. Yeah. I would say that the time that we are alive right now is one of the most exciting times to be alive in space exploration. We need more scientists, we need more engineers, we need more people to look up and wonder.
Yeah.
Over the next 10 years, things are about to become very, very exciting. Yeah.
Science is cool.
Science is cool.
Just saying.
Who remembers Bill Nye the Science Guy?
I do. Bill Nye the Science Guy. Bill Nye.
What the other guy think that we could have the Cosmos TV show?
Neil deGrasse Tyson?
Well, maybe, yeah.
I might need to be readjusted.
And it.
The planets are always moving, so we have to continually move the telescope to catch up with them. Yep, it moved.
We're moving?
Yes.
We're moving or they're moving?
Both.
Okay.
Yeah, so Earth is rotating on its axis, and it's orbiting the sun. And just as much, Mercury is orbiting much closer. Venus is orbiting about half the distance between the sun and Earth. Venus is also very hot, but it's almost exactly the same size and mass as Earth. It is actually technically possible
My kitty's name
to
is Mars.
terraform both Venus and Mars.
Do you smell Mars?
This is within our ability over the next...
Hi, buddy.
We might begin those projects in our lifetime.
Bright star then. Is Mars, I guess?
This is a really cool event.
Yeah, the bright planet there is Mars.
It costs $4 to get into the park.
Hey, if you guys are ever watching a sunset and you ever see what looks like a bright planet, a bright star on the horizon near the sun, that's almost always the planet Venus.
Oh.
And the reason for that is if you have the sun here, and Mercury is very, very close. And so the problem with that is the sun is so bright, often we can't see Mercury from behind the brightness of the corona, but you can see Venus. And so anytime that you're watching the sunset or the sunrise, you can very likely see Venus. It's often called the sunset star, but it's actually a planet. Yeah. Did you get to see Mars?
Yeah.
Yeah. If you have any questions, please feel welcome to ask.
Thank you.
You're welcome, my friend. Thank you for coming out, guys.
Can I see Mars?
Yeah. What was that?
Have you already?
Right up there.
Have you already?
Yeah,
You've seen?
yeah.
Okay. All right. I'm gonna take a look.
Often. Yeah, there are a couple objects that are more red. Yeah.
Oh yeah.
That was the
Pale blue
planet
dot.
Venus.
Okay.
Nice, man.
That's so cool. Oh yeah.
Exactly.
Okay. Oh, the moon looks really beautiful right now.
Really bright.
Yeah.
And I was like, these stars are real small. And then you said that one was Mars. And then I'm like, the planet was really
Mars,
bright.
Mars is right through there. It's the clouds are coming over it, but you can actually see it right through the clouds there. The telescope will peer through most of that.
Under the moon. And I'm
Yeah.
like, that's not a star, that's a planet.
That's exactly right. Yeah. Mercury, Venus, Earth, Mars.
I don't know because
Cockroach.
I look at, remember, like, I keep up when there's always an eclipse.
Oh yeah.
To see other planets. That's why I said, like I think the last eclipse, they said you can see what was it, Uranus? Or which one was it that was really, really close?
Mercury.
Oh, it's Mercury.
Yep, Mercury is really, really close.
I forgot all about it. I'm trying to remember the planet.
Yeah, man.
Like,
Yeah.
Did it just disappear or it came back? I heard Pluto, you could see it again.
Yeah.
It was found again because remember they said it disappeared? They said they found it again.
Do you want to know a fun fact about Pluto?
Yeah,
Do you guys remember when Pluto was a planet?
Yes.
And then we were like, oh, whoa, why did they get rid of it?
Yeah.
I was really sad. It wasn't until a few years ago I started studying why did that happen. Well, it turns out we got better telescopes. We started looking out and seeing more and more objects in the solar system, and we found over 100 objects that were larger than Pluto.
Oh wow.
So then we were like, wait a second, well, what are we going to tell our kids? You have to remember 100 more planets or one less.
Huh.
And so if ever somebody is sad that Pluto's not a planet, just remember that the reason is because we found out that the solar system was so much more bountiful than we thought it was before. Yeah.
No longer an event.
Yeah.
Can I look it through? Do you mind?
Oh, please, yeah.
Is that okay?
Oh, yeah.
Thank you. That's okay. No worries.
It'd be weird if I was like, no.
Yeah.
Everyone else but you.
Everybody else.
Okay.
Stream, I have my glowy thingy from the Charro Days parade.
Oh, that was so much fun.
Yeah, that's so fun. All right. Which one? This one? This one?
Yeah, you can look through both of them.
Knock it.
So this is initially for sighting.
Okay. Oh yeah, there it is. Hi, future home.
Well, that's what I'm saying.
What's up? Cool. Okay, sighting.
I moved here after engineering graduate school to help build stuff with SpaceX. I have every intention of living there one day.
Oh yeah.
Yeah. Jessica too.
Sorry.
I'll see you there.
Huh?
I'll see you there.
Oh yeah. High five.
Yeah.
Yeah, I'm going.
Yeah.
I'm bringing my cat Mars though.
Yeah.
As long as Mars can come.
If you ever need to do physical training, let me know.
Okay.
I do that.
All right. You said the observation, or what are they? What is, the red?
You've never been here?
No, I've never been here.
Oh, I'm so excited.
This is my first time.
Okay. Oh, you'll be like a kid in a candy store.
Okay.
So if follow the red lights we have set up for the night.
Okay, we're gonna follow red lights.
There'll be a presentation. Our chief scientist, Richard will be making a presentation soon.
Okay.
And then keep following the red lights, and you
Okay.
can walk into the observatory, and you can actually see through the telescope. I think they were looking at the Orion Nebula.
Am I allowed to bring a camera inside of there or no?
Oh, absolutely.
Really?
Yeah, totally open to the public. Have fun.
Woo! Okay, I'm gonna snag your mic.
Yeah, go for it.
Thank you for talking to the stream. Say bye, stream.
Oh, bye, stream. I didn't know I was live.
Sorry, I should have warned you. All right.
What is it pointing at? That's a great question.
Okay.
That's Mars. Yeah, that little red dot.
Oh yeah. Here's your water.
That's a great question. What are we looking at? So Mars is. Thank you so much. Mars is the fourth planet from the sun, and it's similar size to Earth. Venus is the second, and it's almost identical in size and mass.
Okay, everybody.
If we were to jump on Venus,
We're gonna walk make a trek. Service may go in and out, so we'll see.
you'd be like superhuman powerful. You'd be twice as strong because the gravity is not as much. You need to bring a jacket. It's a pretty cold place.
Chilly.
And the atmosphere is very, very thin for now.
Okay, here we go.
It's not too cold. During the summertime, it's about as cold as that.
I do want to see the little dude. Why, hello, little dude. There he is. Brother from another mother right there. I think we look similar. What do you think? Let me go next. We'll do a family portrait again. Here we go. Ready? Okay, let's look. Okay, let's see. Waiting for the stream to catch up. This is, by the way, this is a really beautiful swag. South Texas Astronomical Society at S.T.A.R Society RGV. The shirt. It's a cool shirt, right? Who's having fun so far? Let me know in the chat if you are enjoying this. Hey, what's up, Coop? Yeah, this is pretty fun. Let me turn the
Are you taking pictures now?
I am taking video. Live video, yeah.
I'll be like,
Okay. There we go. Okay, we're gonna go to the observatory shortly. Here we go. Cheese. I'm hoping that can be the thumbnail. I'll pull a screenshot. If you had a question for an alien, what would it be? Anybody have any questions? What would be the first question you ask to an alien? Come in peace. Hey, Juan, Spooky de la Garza. I thought you might be here. So I tagged you in that post. Thanks, Perpetual. Hey, SB Shepherd. Okay, let's do a K-dot here. Ooh, my legs are sore. All right, crack, crack. Let's keep going. I'm attached via battery pack to my streams pack, so I need to remember that as I'm walking. Thanks, Unky. All right, let's make a move over to the observatory. that sound good, everybody? Let's do this. Whew. Just confirm we're all sealed, secured, ready, and here we go. I guess I should go this way. This is cool. Path lighting, right this way. Show you what it looks like here. Ooh, this is really cool. Okay, we're going that way. Sound good? Thumbs up, everybody? All right, let's do this. Cool. Do 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 do. Oh, the observatory is back there. That's so cool. And then we're going to have a presentation here in this area. Excuse me. This is so cool. Real quick in case I miss it. This is neat. It's going to be a presentation there, but we're going to keep going to the observatory. Here we go. Oh, this is so cool, everybody. I've never been into I guess I have been into one. Oh, there's a dog outside. We're going into the observatory here. This is so neat. Check this out, everybody. Probably can't see that, but it's really dark. So there's some little smaller observatories over there, that direction. Okay, we're walking in. Here we go. Here we go, here we go. I'm ready. Who's ready? Why am I whispering? I don't know.
What you see are not stars. Stars aren't that dead because they're part of the
Cool.
What we have here is what we have is that you saw noise. We're looking at space, but we're looking at a lot of noise. The camera, the CCD is very sensitive. So it makes everything. So what we have to do is filter out what we don't want in our image. So if you look at stars, we see a lot of little specks, flashes, or spots or artifacts, anything. We might get rid of that because they'll mess up our image. NASA does it. ESA does it. CSA does it. Everybody does it. They, European, NASA, whatever. I even hear Mexico is going to have a thing. Really? I'm not. Everybody told me, right? Seriously. That's what I heard. Mexican there. So, yeah, they're very specific. So what's going to happen is
It's cool. It's a touch screen.
it's the same size everywhere you go. Okay? We use technology like this to give us an image, a certain field of view of one object that we focus on. To perform astrometry on the light characteristics to determine what the coordinates of the picture is. Which way we're looking, up, down, left, or right. There's order in space. We know exactly where we're looking. We have coordinates in every object in space. Now, I mean every location. We don't know what is that every location. It's infinite, but we can't look at longitude this or latitude that.
Scoot in a little more, Mom, because she's taking pictures.
Oh, it's okay. Yeah, it's okay. Thank you.
We know where it's going to be 150 years from now. We know where it's going to be. Okay? So, based on the equations and the databases and the technology and the programs, we know exactly where Jupiter's going to be 10 years from now. Right? It has a very specific goal. Unless something bigger than Jupiter is found, it can actually project it out of the orbit. So cool story, yeah. Okay, so remember, the cool thing about Jupiter is nowhere near as big as the star. And will never be an exoplanet.
This is so neat.
Like that Starship, right? What happens is, Jupiter will never be a star. It's a failed star. It has a lot of gas, but it never ignite. It didn't have enough mass and material to start to do the
Jesus, that's big.
Oh, gee, it's like what, 8 hours?
Oops, sorry. Just want to show the, here's the telescope right there. Right here.
So one thing that's cool about Jupiter is that they call it the guardian of Earth. Because when Earth was just being formed in the early solar system, there were a lot of different rocks moving around, which is what slid the Earth to create the moon. So what happened is all these asteroids were flying around the asteroid belt. All of them.
Oh, wow, cool. Stepping down. Oh, that's a big step. This looks like the movie Signs. Ready? Here we go. There's a ton of, they all look like hard hats. And there's the big one right here. That's the top of it. Okay, all right. I'm gonna go over to the other presentation. Here we go.
I'm sorry.
Hey, you're fine. No, you're totally cool.
I know over there you were like, you called me and then I got...
You're totally cool. You're totally cool. It worked out great.
Are you doing well?
Yeah, doing really well. Thank you. This is so fun. Okay, we're going to the presentation. This tripod is heavy.
And each of those images is a representation of the surface of the sun as well as its atmosphere. This was the Yuko satellite, which was a joint mission between Japan and the United States. And there's something that I want you to notice here is the sun looks very different from year to year, especially when you're at the top part there. So I don't want to cause any feedback from this. So right here, you notice from here to here, there's quite a bit of a difference. This is representation of the sun's stellar its cycle, which happens every 10 to 11 years. You might have heard of solar activity and such like that. So this is a representation of that. And it's kind of a foreshadowing of things to come. So let's talk about the sun a little bit. How many people are familiar with the sun? I think everybody is in some regard, right? Does anybody know what powers the sun? What makes the sun so bright and last so long? Does anybody have an answer to that? Yeah.
No.
The core. So the core, which you see right here, I have a laser pointer. So the core, there. What's happening in the core? Do you know, or does anybody know? It's burning hydrogen. Yes. And if you know anything about burning hydrogen, you have to make a very high temperature. So it's about 15, 16 million degrees at the center of the sun. That's hot, but it's not actually as hot as things get in astronomy. But it needs to be that hot to produce nuclear fusion. So that's the power source of the sun occurring at the center, and it's causing all of the other stuff that happens down to its effect on the Earth is really caused by the nuclear fusion, the power inside the sun, which is generating all of this change. Then we have the radiative and the convective zones. These are different layers of the sun where the physics kind of changes, but basically you can imagine that from the core through the radiative zone. This is where most of the energy is radiating. That's why it's called the radiative zone. But you basically have this spinning disk that's emitting energy. Once it reaches the convective zone, you have convection cells, almost more like boiling water or some sort of other convective cell that occurs on Earth, that rotating these very deep rotational currents inside the sun, which bring the high energy from the lower parts up to the outer parts. And then you have the photosphere, which is the visible surface of the sun. That's something that we can see usually with the optical eyes or optical telescopes. But there's also a protective layer that prevents us from seeing it in certain wavelengths. And that's the, well, we have the chromosphere, so right here, which is the atmosphere of the sun. And then the corona, which is the outer part of the atmosphere of the sun. That's usually visible during a solar eclipse, by the way, which we'll see in a bit. And then we're going to go into a little bit. So there's a couple of these features on the surface of the sun. And these are related to the space weather that I'm going to talk about. So I'm just going to zoom in on a couple of these and we're going to learn about different features of the sun. So this is a zoomed in picture of the surface. This is the photosphere. This is taken, most pictures of the sun are taken in ultraviolet, and there's specific reasons why, which we can get into, but basically most of the pictures you see are false color representations, but they are representative of what the sun actually looks like, just in a slightly bluer light than we're used to. So this is the surface granulation. This is what tells us that there's convection currents going on below, because you have the surface granulation. Each of these cells are about 1,500 kilometers in length, so you can think about like continent-sized cells, and they last 8 to 20 minutes long, 30 minutes long until they start to change. So this is a very this is a very changing scene. This is a snapshot. But if you zoom up on the surface of the sun, it's not actually a smooth ball at all. It's actually got these convective cells that are quite big. Underneath these cells are super granular cells, which are 30,000 kilometers in size. So the size of the Earth. And they're creating large flows. They're bringing the energy up to the surface. So it's a very interesting feature right off the bat. You zoom up onto the surface of the sun and you get these really interesting granulation features. You also get sunspots, which is a very, I think, one of the more familiar phenomenon.
You're good.
You still see the surface granulation here, but there's a new feature. Or some sort of dark hole.
It's like a sunflower.
Really what you're seeing is deeper into the sun by a few hundred kilometers or more. What's happening here is the sun has a very strong magnetic field, and the places on the surface of the sun where the magnetic field breaks through, it pushes the plasma out of the way. So what you're seeing here is in the center, the strongest component of the magnetic field. You could think of a magnet in that way, pushing the material out. And then on the outer parts here, the magnetic field starts to bend and get weaker. So you see kind of a, not so much a dark patch, but basically everything within this patch here is a few thousand degrees cooler than the surface is. So this is still hotter than lava, but the surface here is about 5,700 degrees. This is maybe 3,000 to 4,000 degrees, so it's still pretty darn hot.
That's hot.
Now, sunspots are really interesting because sunspots, so before I get to that, sunspots basically are indicative of solar activity. When there's very little sunspots, the sun is in a very quiet state. If I go back to that picture really quickly at the beginning, that would be like this case here at solar minimum, when the sun is not as active as it would be at, say, solar maximum. When you're at solar maximum and the sun is behaving very violently, there's a lot of sunspots on the surface. So astronomers typically count the sunspots, and that usually tells where we are in the solar cycle. So lots of sunspots mean it's going to be very active. I won't talk about this just yet. So one of the big features of the sun are these coronal mass ejections, these solar prominences. So extended features that come off of the surface of the sun. Now, the sun, by the way, is 109 Earth radii, in its radius is 109 Earth radii, so you can imagine this is several Earths in size.
Wow.
These are huge explosions. And what they do is the magnetic field is very unstable. When it becomes unstable, some of the plasma detaches from the sun and gets shot out into space. If that happens to be facing us, it can cause some problems. And actually, we're currently going through a solar storm at this very moment. We're in the tail end of a solar storm, which I'll show you in a bit. I'm building up to it because you need to see some of the features of the sun to understand what's producing these effects. Coronal mass ejections are pretty much the most violent thing that the sun can do. they send charged particles out. I don't know if I have a GIF of it. In a few slides I do. But basically they move at several thousand kilometers per second. So they can cross the continental United States in a split second. That's how fast these explosions actually occur. And when they hit the Earth, they cause the magnetic field a lot of tension, a lot of disturbances, which corresponds to radio blackouts. Your radios might not work, internet might be slow, all the way down to actually electrical shocks because the wires get overwhelmed by so many charged particles. The aurora are another thing that you would see. So aurora get very strong during solar maximum, and they get very weak during solar minimum. And aurora are very strong when one of these things hit the Earth.
Cool.
Now during an eclipse, you can see a very interesting feature, which is the corona, this outer part right here. This is the extended atmosphere of the sun. It's actually a mystery because I just told you that the center of the sun is 15 million degrees. The surface of the sun is 5,000 degrees. But for some reason that physicists still don't really know why, the corona is millions of degrees. Something is heating the corona more than even the surface of the sun is, and we don't fully understand why. So it's just pointing that out there for future physicists and astronomers. The sun is still a mystery in a lot of ways. We don't understand why the corona gets to be 1.5 million degrees, but you get to see it, and like Earth is going to be very, very small on this screen. So this is millions of miles of atmosphere that extend from the sun. Yeah, it's just very beautiful, and you can see, it might not be possible to see, but on the edges, and in this particular picture, it's really only here. During a solar eclipse, you can see some of those explosions, those solar prominences on the surface, when the sun is blocked by the moon. One just important piece of information, this might be the most complicated slide I show, but it's still very relevant. Apologize for the brightness here. The center of the sun is powered by nuclear fusion. That's really just because there's a lot of mass that are falling down, and at some point it heats up to the point where the mass doesn't fall anymore and it gets pushed back by pressure. That pressure is very high, and really you need to fuse hydrogen together into helium to produce enough energy to keep the sun from collapsing further. So this is just a kind of a diagram of what's going on, but you're smashing ultimately 4 hydrogen together to produce helium and some energy. The sun is 3/4 of its weight is hydrogen, and 25% is helium, and the rest is just some metals essentially. So a majority of the fuel source is still there for another few billion years at least. So sunspots have actually been observed for quite a while. This is the earliest recorded observation of a sunspot by John of Worcester in 1168 AD, I think. A very interesting picture, although not very astrophysically relevant, because you can't. I wouldn't know how to interpret this picture, but it's technically, and from what I read, is the earliest sunspot that has actually been recorded. So these go back hundreds of years, if not a millennia or more. We've been counting sunspots since, well, scientifically since the 1600s, since basically telescopes were invented in the early 1600s. And it's actually really easy to count sunspots. You basically need to block enough sunlight so that you don't blind yourself or destroy your telescope. And you wake up every day, you point your telescope at the sun, and you just count how many sunspots you see. And you plot it. And what you get is this really interesting feature. Ignoring the black line, you see these peaks and troughs, and they occur on decade, 11-year cycles. So this is that like solar maximum, solar minimum. We're currently entering into a new solar maximum in the next 2 years. So in 2025 or so, that's predicted to be the next peak of activity. But some interesting things is, like, for instance, the last century, the sun's been much more active than it has been in the past. This black line, for instance, is the average of that year. So you could see that there's much more activity during the late couple of centuries than earlier. That, by the way, is really interesting to me because, you know, people who are interested in climate and the effects on climate, the sun is arguably the most dominant dynamical force in the solar system that affects the Earth's atmosphere, which could affect crops, it can affect agriculture, population, and et cetera. So paying attention to the sun's activity is actually very relevant. This is actually, and we know all the way back to 10,000 BC, but you need to be a little bit more creative to get this plot. And we know that the sun has been, this, by the way, means the sun's been pretty stable. This looks like it's going up and down, but if you notice, it's pretty much riding in a regime around 40 or 50 sunspots is the average that we see on the surface. And this is using radiocarbon 14 dating. So
the sun does affect the Earth in some ways where we can measure past behavior. Even before humans were observing the sun with telescopes, we can find proxies on the Earth to predict how the sun behaved in the past. And our final plot I'm showing here is the most recent situation. So red line is the predicted basically solar cycle. And these are measurements. So on the y-axis is the number of sunspots. It's just the number I'm counting. The x-axis is time. So this little plot down here shows the past behavior that I just showed before. What's interesting here is the sun just woke up very rapidly. It was following prediction for a while, and then only in the year 2023, it's actually been a lot more active than predicted. And I'm about to show a few examples of the last week or so of the effects of this. It's quite remarkable what's happening on the sun. One of the instruments that a lot of this data come from, this is the Solar Dynamic Observatory 2010. It has a set of filtered cameras up here that observe in different ultraviolet wavelengths. It's got its solar array for for power, and it has this helioseismic and magnetic imager. So these sunspots, which I told you are magnetic field lines, we can map the magnetic field of the sun and we can learn more about its activity that way. So a couple of different instruments on here, another UV camera, this EVE camera, which is designed to detect variability, how the sun changes, and then a high gain antenna to transmit the data back because we need to send it back to Earth. This is just an example of what it might see. These are all different color filters that are being placed in front of the camera, and then we take a picture. And each color tells you a little bit different about what's going on. For instance, these ones down here tell you where all the active regions are. So these wavelengths, what this means, this is all, these numbers basically mean ultraviolet. So we observe at the observatory over here in optical. If you go to the blue side of optical, past where we can see, you're in the ultraviolet. So all of these are mainly ultraviolet light. But what we're seeing down here is like solar activity. Here we're able to see just the surface of the sun and the sunspots more clearly. So different layers depending on the filtered light you're using. These solar observers in space are very crucial for understanding it, and also because it would be hard to observe the sun from the ground this well. But this teaches us all the stuff we know about the sun. It's the most studied star because it's in our backyard. This is a
So that's funny.
So that's the background on the sun. Are there any questions at this point? Because that was mainly like the theory slash background before I start talking about like what's been actually happening lately. Yes, sir?
Is the sun explosion destroy the whole universe?
No, it would not destroy the whole universe. The sun won't explode, and we have a good reason why we think it won't explode. The sun won't last forever, but it's considered a dwarf star. It's a yellow dwarf star. And dwarfs don't explode. They run out of fuel and they swell up and they get bigger and then they just dissipate.
Expand.
And they leave behind a dense core called a white dwarf. The stars that do explode, that for a couple of seconds, they outshine the entire universe. And in the observable universe, there's about one supernova every second.
Wow.
So you can imagine how many explosions there are right now.
That's a lot.
One supernova per second in the observable universe. Now, we can't observe all of that, but what we do see are supernova every single day. At the observatory here, we hunt transient sources, so things that explode and disappear, things that appear where they weren't before and disappear. So these types of explosions, astronomers are finding these types of objects all the time. So supernova occur all the time, and they outshine the entire observable universe for a few seconds. I was telling you all about Betelgeuse. If that went supernova, which is expected to, any time now, astronomically speaking, we would lose night for a month.
Oh wow!
So these are very bright objects. This was taken about six or 7 hours ago. Basically earlier in the day. This is one of the images that the Solar Dynamic Observatory, the SDO, can see, and they're counting sunspots here. So you can see sunspot 3,258, 259. So they're counting these sunspots. And right now, we're noticing the sunspot number is increasing, which is what we expect. The sun is increasing in its activity. These sunspots were on the opposite side of the star, a week and a half ago. Something interesting happened during that time. So this is zoomed up on one of them. This was taken on the 18th, so
Look like
almost a week ago.
sunflowers.
But this was on the limb of the sun. So basically when these were over here coming into view, we had somebody on the ground, Alessandro Gambaro from Italy. On the ground, he took a nice picture of one of these sunspots up close with, he told all the type of telescope and everything. So if you want to replicate these observations, you can. But these sunspots were causing a lot of activity on the surface of the sun about a week ago, and they started to affect us this week because it takes some time for that to get to us. Here's another view of the same thing. So going back to this is the same picture, but just in a different wavelength. Right here, we're seeing it in kind of an ultraviolet light, where we're seeing that the chromosphere, the atmosphere. You're seeing a hole in the atmosphere. That tells you right away that basically that protective atmosphere has been opened up by the magnetic field, and high energy particles are free to move out of the sun. So if this is aimed right at us, it's basically like there's just open charged particles coming straight at us. Our magnetic field does protect us, but basically what this is like a prediction for a forecaster. Oh, we see this giant hole in the sun, so in 3 or 4 days we're expecting turbulent weather, essentially. So that's really how they predict. There's solar predictions, daily solar predictions. A lot of this is from spaceweather.com, it brings all of these different observations together so you can check it, just like to check the daily weather, perhaps.
That's cool.
The planetary K index. So this is March 25th UT time. So about a day ago or so, this is a solar storm. And every step on this plot is an order of magnitude. So it's not just a little bit. Every time it's a step, it's actually quite a bigger order of magnitude of power. So the fact that these are red right here, what this means is basically about 12 to 24 hours ago, we got hit by this giant solar storm. And it actually caused, if you were in the Arctic Circle, your radio would not work. This could be very serious stuff. The astronauts on the ISS would have to take cover if they got hit directly by one of these. They actually have a lead-lined bunker up in there.
Oh, wow.
The planetary K index basically tells you how far down is the aurora extending.
Oh, cool.
When the solar activity is very powerful, this prominence can reach all the way down. Down onto the continental United States, for instance. I'll show you pictures in a second of people that took pictures over the last few days in the United States. But basically the K index right now is pretty quiet. It's receding up, which means it's getting weaker, and the aurora are only seen up in the northern part of the Earth. But a day or two ago, again, this was all the way down here, and that's the K index. Higher K index means the solar aurora reach further down toward the equator.
That's cool. Very cool information. Oh, cool.
So this is when those sunspots I just showed you were on the backside of the sun, which was around the 13th. We didn't see this, by the way. We could only see basically something blew up on the far side of the sun, which is not uncommon, by the way. But what you're seeing is actually the backside of the sun, something exploding off. If that was facing us, that would not be good. But when those sunspots rotated into view just recently, we confirmed, those sunspots were actually the site of this violent outburst that reached us only a few days ago. This is Mercury, by the way. Oh. So this is called a coronagraph. When you want to understand the explosion dynamics on the surface of the sun, you cover the surface so you block most of the brightness out. You get all the extended emission here. Mercury is there, of course. And all of these particles here are cosmic rays, so they're protons and neutrons hitting the camera from other stars and our sun. Anybody notice what this is?
Tornado! Tornado!
This is from Oklahoma in 1999.
Yeah.
This is an F5 tornado, so highest energy level tornado.
Yeah.
Pretty scary stuff. This is formidable, right? Mother Nature is very formidable on Earth. However, we just observed probably the biggest tornado in the solar system.
This is great.
This was taken 3 days ago on the surface of the sun, and it's a tornado, but it's made of plasma. It's interesting. They form the same exact way,
but they're made of different materials. So convective cells on the Earth,
the group on Facebook, the page on Facebook, I don't know, all kinds of places. I don't know where.
In this case, you have plasma and magnetic fields. This is a magnetic field that broke off of the sun and started wrapping it around itself, twisting the plasma. Eventually, and this GIF doesn't show it, but there's other, you can look this up online, solar tornado. This detached from the sun and just blew off into space. Wow. So there's a plasma. What would the temperature be?
That's so cool.
Around that tornado? It's a very good question because it's rapidly changing. This is surface material, which is about 5,000 Kelvin. Wow. You can think 5,000 Celsius or so. But as this leaves, it's entering that hot corona, which is millions of degrees. So it's very hard to tell. Also, I'm just explaining all the technical details, but when there's a magnetic field present, that energizes it as well. So all of this is going into, this could be tens of thousands, if not hundreds of thousands of degrees. Once it detaches and it flies off into space, it does radiate away and it loses some energy. But if it hits the Earth, it basically interacts with the magnetic field. So.
Ooh, pretty.
So this is an aurora that was taken in Montana just yesterday.
Wow, that is beautiful.
Now, simultaneously in Montana, Nebraska, Virginia. Oh, actually, no, this is the Virginia picture. I'm sorry. No, this is why I'm showing this, because aurora came all the way down to Virginia. People in Montana see them all the time, but this is Shenandoah Valley National Park.
That's amazing.
The sun was very active very recently, and that's the effect of it. You'll see it farther south. Sometimes even into Texas, northern parts of Texas, the aurora will come down.
Wow, look at that.
This is another interesting thing. I just learned this today. This is not an aurora, but it's related. This is called STEAV. And I'm not even kidding you, it's an acronym. It's Strong Thermal Emission Velocity Enhancement.
Whoa.
It's basically a mini aurora that when the Earth gets hit by these particles, the magnetic field normally handles it, but sometimes it's so strong that the magnetic field shifts, becomes unstable, and holes open up. When holes open up in the Earth's magnetic field, particles fly through and they produce stuff like this. So STEAV was seen, this is in Scotland, but STEAV was seen in Montana, Nebraska, Oklahoma, and Colorado just over the last few days. Usually they're like purple and pink. That's usually one of the telltale signs. The other thing is that it's like pretty localized. It's not like this other picture I showed before, where it's a more classic aurora taken. This is a 15-minute exposure, by the way. So
oh wow,
this was taken at like 6 in the morning.
Oh, wow.
Some guy, I forget his name. I wrote it down, but he set his camera up and he took a 15-minute exposure, and this is the result. So
wow, that's beautiful.
Very interesting.
See the stars in the upper left.
Steve.
Cool.
Things you learn sometimes. There's another shot of Steve. I believe this one was Montana and this one was Scotland, now that I'm looking at it correctly, yeah. So you might even glance at this and be like, oh, it's just a cloud in the sky, but it's worth taking a second look. I'm not sure exactly what this is. This could be a very bright star or it could be a planet. I don't have positional information here, but yeah, it could be either one of those. Probably not a comet. Okay, so that's what's been happening over the last few days. In conclusion with this, it's very important to pay attention to what's happening on the sun. There was an event in 1859 called the Carrington event. This is before, obviously, phones and the internet, of course, but there were wires, basically communication lines, telegraph lines that were being used globally. The Carrington event, if I go all the way back, well, it's like 1859, so at the peak of this solar cycle right here, we got hit by one of the most powerful types of coronal mass ejections. Now, this is before the internet, so if this happened right now, our power systems would go off for sure. Your cell phones would not work for a while. People were getting electrocuted when they would touch the telegraph lines all over the world because these charged particles made it all the way to the surface of the Earth. So if this happened today, it would be serious consequences for the economy and for the power system. And frankly, our system is not prepared for that because we haven't had an event like that since. But we're entering into this new modern maximum. So really, even in the next 2 years, we could see record-breaking. We're already seeing record-breaking
activity. The solar storm that just hit was a 6-year record. It hasn't happened in 6 years at this level. So it's just important to pay attention to. Yeah, any questions at this point?
What are they doing to prepare for that?
Yeah. Well, the one thing is, it's really preparing the power grid. The power grid is the most sensitive thing. You know, even if it gets too cold, right, it could, or if it snows a bit, it can damage it. Let alone it's not surge protected to that level. So when these charged particles hit the ground, anything that's electronic will conduct it. And they need to be surge protected. But it's not necessarily a priority because there's not normally surges of this level until there are, and then you would have wished that you prepared for it. I'm also not an engineer in that regard, so I don't know how the power system specifically would be protected, but I know that one of them is just basically surge protecting it against charged particles from the sky.
All right, we're going to make a move.
Yeah, I mean, thankfully we have a magnetic field too. Most of the other planets in the solar system that are rocky don't. So the surface would be like we're getting a good shield. I just showed you a bunch of interesting dynamics that are only occurred over the last few days. That's just the sun though. There's so many other types of stars in the universe. And they're very exotic. I mean, look at Betelgeuse, which is the big red, almost like the background itself, right? What happens when I put Betelgeuse where the sun is right now? We're inside it. Mars is inside it, right? And Betelgeuse is not the biggest star we know. Rigel, I mean, all of these we just pointed to tonight, by the way, like in the sky. So Betelgeuse, Pollux, Sirius, Rigel, Aldebaran. All of these stars are right up in the sky. They're all completely different. And it begs the question, well, what happens to them? They have nuclear fuel, but they run out eventually. You know, we had a good question, will the sun explode? That's actually, it wasn't obvious for the longest time. Stars like the sun, which I think you can appreciate on this plot, stars, there's kind of two main types. There's these dwarfs, and then there's giants. That's actually what they're called, dwarfs and giants. When you look at the population of stars and you plot them, you get an interesting diagram. And it might, this is kind of hard to see, I apologize. It's called a Hertzsprung-Russell diagram, and I show this a lot. It's one of the most important plots in all of astrophysics. Like, there might be one or two plots that are more important than this. What this tells you are all the different types of stars and what becomes of them, right? The main sequence, which is this line right here, these are stars like the sun, or bigger, or smaller, but they're still burning hydrogen. They're still in their main life cycle. So our sun is a middle-aged star. It's about 5 billion years old, has about another 5 billion years estimated to go. The sun would be at the center of this plot, so it says luminosity, sun equals 1, so we'd be right here in the center. Kind of interesting. We did not design this plot to be in the center, by the way. It's logarithmic based just on what we observed. Cool and small stars are here. Majority of the stars in the universe are red dwarfs and orange dwarfs. And then up here are your bright blue main sequence stars. And then you'll see that there's this population that, but you run out eventually. And we know the age of the star based on how early it peels off. So the giants end up here, and the main sequence are here. Now, if you're low mass, and I think I might have a, yeah. So if you're a low mass star like the sun, this is Sirius A and Sirius B. So Sirius has an actual binary system, but it's a bright star, a main sequence star, and a white dwarf.
So bright.
The little star down there is a white dwarf. That is what our sun will become. It's just the remnant core. So the sun's going to run out of its energy. It's not big enough to collapse and explode, so it just kind of dies in a very humble way, essentially. It just dissipates off. And what's left behind is this dense little nugget, this core called a white dwarf, which will last longer than the universe has existed so far. They do cool, but they don't cool like a normal thing cools off. So they take a long time to cool. And of course, and this is my last slide because I wanted to, I couldn't not talk about black holes, but
black holes.
If you're a big star, you do blow up in a supernova. Now there's different types of supernova, but at the end of the day, the star runs out of fuel, it gets exhausted, and it collapses. If it doesn't have any remaining fuel source, it just keeps collapsing until it squeezes the atoms together into, well, a couple of things. They can be held up by, like a white dwarf, for instance, is the next thing. So that's about the size of Earth, but it's the mass of the sun. So very dense core. Now, if you have a bigger star, you can compress that even more, and what happens is all the atoms squeeze into each other and all become neutrons. You might have heard of a neutron star. The sun will not become a neutron star because it's not big enough, but if it was bigger, it would collapse and it would squeeze that white dwarf even more. Again, the mass of the sun, but this time the size of Manhattan. Wow. So a 10-kilometer sized star, very dense, a teaspoon of it weighs more than Mount Everest. Right, a sugar cube is 1 trillion grams. It's beyond comprehension. These are dense objects, but that's not the last step, because if it's even bigger, there's no known physics that prevents the collapse further. So once the neutrons are overwhelmed, there's nothing left in physics that we know of that can hold up that collapse. So you get a black hole. And a black hole is the result of the most massive deaths of stars. The thing about a black hole, they weren't always called black holes. They were originally called collapsars. Even in the 60s, they were called collapsars. Why? Because the star, that neutron star, keeps collapsing. Eventually, it collapses so far down that we can't see what's happening anymore. That's the black hole. But inside, it's still collapsing. We just don't have any physics to explain what's inside of it. So maybe the next astronomers in the crowd here will be able to answer that question. But this is the result of pretty much all of the major stellar evolution in the universe. So kind of want to give an overview, mainly about the stellar situation in our solar system, but then kind of open it up to all the different other possibilities. So thank you for your time. But if you want to keep talking, I'm here. So yeah, thanks very much.
Thank you. I have a question.
Stop for burning questions.
Question.
And pyramids too, but I don't want to take up too much.
I have a question.
Yes.
What are sprites?
Sprites?
Yes.
I don't know.
Like the red, they look kind of like what are they called? The S.T.A.R or the S, what was it called? The aurora that kind of made the...
Oh, the thing that I showed on here?
Yes.
Oh, Steve.
Yeah, the Steves.
That's the most fun name. Yeah.
I love it. How do you spell it?
It's like S-T-E-V.
V-E, Steve, okay.
Strong thermal emission velocity enhancement.
That's cool.
I just learned it today, so.
Okay.
Telescope with the acronym GRANDMA.
Oh yeah,
Grandma.
So I'm part of the Chorus collaboration, which is like this scientific network that's trying to hunt these explosions, and there's a competitor called the Grandma Collaboration, which is an acronym, by the way, which is really, really fun.
Yeah, I come up with fun acronyms. How long does that how long is it visible?
So sprites are visible during lightning, thunder and lightning storms. Everybody.
I just learned about it today, but these change over a few hours, because this is dissipated energy into the atmosphere, and once it's in the atmosphere, there's plenty of places for it to go. It's going to be pretty transient, but I would say you'd see this changing over, let's say, the order of hours.
That's so cool.
The color tells you, by the way, what type of atom in the atmosphere it's hitting, right? So like if it's green, I believe it's nitrogen. And if it's a different color, it might be oxygen. So these photons are coming in from the sun, and then they strike an atom in the atmosphere and they make a reaction. The color tells you which chemical it was hitting at that time.
That's really cool.
That's a great question. Well, black holes are, they vary. There's mainly two types of black holes. There's stellar black holes and there's supermassive black holes. Stellar black holes are the ones I just told you about, when a star dies and it blows up and it's massive. Let's say it's 20 times the size of the sun, or 40 times the size of the sun. That will blow up and it will create a black hole. Those black holes are about 5 to 10 times the mass of the sun. And they're pretty small, to be honest. They're like, a neutron star is the size of Manhattan. Black hole is going to be even smaller than that. But it's such an efficient engine that it's very powerful over long reaches, right? Supermassive black holes, on the other hand, they're produced by kind of ancient processes. They're found at the center of galaxies, so you might have heard that the Milky Way has a black hole at the center of the galaxy. That is not the result of a dead star. That is the result of, well, we're not exactly sure, but we know that there's a supermassive black hole at the center of every galaxy, and these are bigger than the solar system. So there's some that we see billions of light years away at the very early formation of the solar system, way out there, that are 1 billion times the mass of the sun. Like legitimately 1 billion times the mass of the sun. If you were to place them where the sun is now, they would be, Neptune would be inside the black hole.
Wow.
So black holes can be very large. There's no limit to their size. And we're not exactly sure if Stephen Hawking was right because we haven't tested it, but he predicted that a black hole left to its own devices will actually dissipate for trillions of years. But they're usually consuming, and as they take in matter, they grow. So black holes grow proportional to the amount of matter they consume. As they consume matter, they get bigger. So they grow, and they can actually merge. So two black holes, like which we've detected with gravitational waves recently, when black holes find each other, they kind of into each other, and they grow into a bigger one. And this is happening all the time, like all the time, every second or minute. There's something like this happening.
All right,
That's a great question.
Thanks.
Well,
When S.T.A.R was born, how far has it traveled?
that's a great question. Wow.
Can you repeat that?
Since our sun was born, how far has it traveled in the universe? This is a challenging question. I'll tell you what I know, that the sun is moving something like 20 kilometers per second relative to the nearest stars. When you're talking about velocity in space, you need a reference point because there is no absolute reference point. So compared to the nearby stars, we're moving something like 20 kilometers per second. So
from the stream?
Earth is going around the sun, and then the whole entire system is projecting into
cool.
space at like 20 kilometers per second.
Thank you. I don't have
Then
service.
on top of that, we're rotating around the galaxy, and the galaxy
Thank you,
is
Julian,
200
for asking.
kilometers per second. So we orbit the galaxy every 200 million years. So during the Triassic era, when there were triceratops on Earth, we made it around the Milky Way since then. That's what I know from that. I mean, the Milky Way also moves through space, and then the Milky Way is part of a galaxy cluster, and that's moving through space. So at the end of the day, we don't really know, but we can count up the velocities, and you can make a simple assumption if the velocity never changed, which is, it's a simple assumption, but it gets you somewhere. Then we know that, okay, the time is 5 billion years. The sun's been moving at that speed for 5 billion years. I can calculate the distance for simple high school physics, but it's probably not accurate. So, yeah, that's like, I never got asked that question before. That's a really good question.
Sorry, everybody. The stream feed is dropping right now. It's going up and down and up and down.
As in, like, is a galaxy limitless itself, or are there galaxies in every place? Like,
oh wait, no service.
I see what you're saying. No, it's a good. Galaxies are very hard to define in some cases because they don't have a cutoff. Like, it's not like a border, and then you're in intergalactic space, and there's nothing that. You know, galaxies are always in clusters. Galaxies are never alone. So Andromeda Galaxy and Triangulum, which are our two nearest neighbors, they're all gravitationally attracted to us. So we're all in a system, but in between the galaxies, there's this hot gas, million-degree gas. And not only that, the galaxies kind of merge with each other over time. We know that the Milky Way, our galaxy, has absorbed other galaxies. We watch galaxies getting ripped apart by other galaxies all the time. So galaxies are interacting and physically in contact with each other. So it's not really an easy question to answer, but there's kind of a way to say, like, this is the galaxy and this is not the galaxy. But in the scheme of things, everything's kind of interacting, right? Even the Andromeda Galaxy, which we're told we're going to collide with in, I don't know, 1 billion years. I'm not exactly sure. It's so far away. It's 1 million light years away, but we're already starting to physically interact with it. That's how big these galaxies are. Right. That's a good question, too.
Earlier you said that there was a hole in the magnetic field around the Earth.
Yes.
So the Steve comes through that hole, or the Steve creates the hole?
Steve, from what my understanding, comes through the hole. And
Why would that hole be created?
well, you know, the magnetic field is kind of like I mean, you could think of it like a shield, and then as the Earth is moving, it's kind of like tapered off on one end, kind of like a tadpole. It also has a polarity, right? It's like a magnet north and south direction. The sun also has a north and south direction, its own magnet, right? we can't. So when the sun's magnet changes, sometimes it flips, and so the north and the south are anti-aligned with ours, and that causes a cancellation. When you rotate the two magnets together, there's now an attractive force that actually cancels field lines. So in other words, the sun rotates its magnetic field just randomly. We can't predict it necessarily. That interacts with ours. They kind of neutralize each other. They kind of cancel each other, and that's where these holes are formed. But it's a very complicated dynamic system, though. If you look at what the magnetic field actually looks like, there's some pretty interesting features. It's very hard physics, but yeah, that's my understanding. No, and it hasn't been in the past. So one of my favorite examples for this is the Great Pyramids of Giza, right? There's the 3 pyramids. And if you're in Khufu and you're looking through the main shaft, there's 3 shafts. One of them is aligned to Orion. The other one is, quote, North Star. But when you look through it, Polaris is not in that star, or in that alignment. If you go back in time and you rotate the sky accordingly, the star Thuban, which is a North Star, it's up there, was where the North Star is now, and it would be perfectly aligned through that pyramid shaft. So that was aligned to the previous North Star. The fact of the matter is that the Earth, it wobbles like a top. So it's spinning 24 hours a day. It's going around the sun 365 days a year. But on top of that, there's other motions. It's like wobbling like a top. And that wobble sweeps a circle 26,000 years. So it's a very slow wobble. But as it rotates through, basically what that means is the North Pole of the sky rotates in a circle, and that circle is 26,000 years. So Polaris will eventually rotate out of where it is now. It's just in a chance alignment with the true north. So in a few thousand years you would see it. But the North Star has been the North Star since at least the Romans, I would say, because over time it does change quite a bit. Actually, yeah, the Romans, because the Romans thought the pyramids were ancient. That's the way I think of it. Like the pyramids are older to the Romans than the Romans are to us. So that's the amount of time you need. You need like 5,000 years or more.
I missed that part. How do those form? You said those are called Steves, right?
They're called Steve, yeah.
Nothing like the Borealis?
It's similar. It's like a detached Borealis. It's like a chunk of plasma from the sun, found its way through a hole in the magnetic field of the Earth, and then like dissipates through the atmosphere. Whereas in the aurora, that's charged particles reaching the north and the south poles, so the Australis and the Borealis. Positively charged particles coupled to the north, negatively charged particles to the south, like a magnet. So they are similar, but they are different. I like these questions. Keeping me on my toes.
I'm impressed. Thank you very much.
Well, thank you for your time. Yeah.
When is your next event?
May 5th, we're going to have one
May 5th.
For the 5th year anniversary of CTMO. Victor's birthday as well.
Oh, nice.
and yeah. So
thanks,
yeah, May 5th.
Juan. Appreciate you very much for posting screenshots. Awesome.
Do you have anything you want to say? Yeah, thank you. Sure.
All right, let's go see if there's anything else to check out.
Like terraform? Yeah, that's a good question. Mars is the one that's the sole focus right now. There's reasons for that, but there's other planets. There's other ideas I've heard for different planets, but they require a more creative strategy. For instance, Venus is closer to Earth in all forms than Mars is. Mars has a 25-hour day. That's about it, but it's much smaller. It gets much more radiation at its surface, and it's colder. Venus, yeah, you can't live on the surface because it will melt lead. But there's an atmospheric layer where
could actually float there and have like floating cities. Actually, Carl Sagan invented that idea, as well as in Jupiter as well. So every planet, there's kind of a solution that's been proposed where, oh, if we had to colonize it, there is a creative way we could do it. On Mercury, you would have to be on the far side where you're not on the sun side, which is plus or minus 400 degrees on each side. So most of the so Mars is like the least hospitable. When you're on the equator of Mars during the summer seasons, Ray Bradbury taught me this, who's a sci-fi author, right? You could, in principle, wear just a face mask and goggles because it is like 70 Fahrenheit at the equator on Mars during the summertime. During the peak day, summertime months, which is very rare. Now, also during those months, there's 250 kilometer per hour silicate slag hurricanes, which would powderize concrete. So you can't walk outside most of the time because it's not soil like this. It's like red because it's iron rusted, and that gets thrown faster than a hurricane does. So the material that you need to build on the surface of Mars is going to be very different than here. But I guess in principle, the moons of the planets are probably easier to colonize than the planets themselves, like Jupiter's moons.
Oh, that's cool.
Because Jupiter, for instance, just like the moon, our moon, causes tides on the Earth by basically pulling on the Earth. Jupiter is so much stronger, it liquefies the insides of its planets. Like Io is volcanic only because Jupiter is causing it. It's like it's messing up. Io is too small to have its own magnetic field and its own dynamo. It's induced entirely from Jupiter. So the planets can cause moons to be actually more habitable than the planets themselves. Earth is still the best thing.
Haha.
Solar flares. They do, and so do coronal mass ejections, yes.
That's the Northern Lights, isn't it?
Yes, and its name is Steve.
Steve.
This is Steve.
They're in Alaska, and then they're in Antarctica on the bottom.
Oh my gosh.
Yep, and this is this one's Norway in particular, I think, or what did I say, Scotland? I forget exactly.
Okay. Thank you.
Anything about black? Oh wait, no, one black hole question. I mean, I'll be here.
Oh, cool. Love the lights.
Did everybody see the telescopes? Because I think it's probably died down now enough we can see it.
Yeah, if you haven't gone into the observatory, you should definitely check it out.
Yes.
So I guess those are your remarks. Thank you all for being here. I'm so sorry that the last hour got a little bit clouded out.
Okay, we're headed this way. Here we go. Telescope time. Telescope time.
I was there. No. But was the lady that he was talking about? Was she there?
All right, thank you.
That's a cheese.
That was like that, he died, or that really sick as well. I'm like, my husband's dying, so he can't help you right now. I'm sorry, it's great and stuff. And he never responded. And that waited, I think, like a month. Finally, I went to the next guy, and I was listening, hey, he responded on the day. Hey, email, Dr. Phil, hey, what's up, man? Hey, he said something to hold you. He goes, nothing. So I formed a term about that, no data for my concept inventory. So I went over to another website on a repository, and so Mario was like, dude, you're going to stay here for summer. Summer one? Yeah, summer two. Okay. so then the doctor was like, no, you're going to stay here for fall.
Doing research right now in there.
You'll do it. Trust me. You're smart. It'll happen. But, I was...
That's cool.
I almost didn't pass it.
It's Coop and Nick.
So I'm working my new...
I think that's Coop and Nick in there. All right.
Yeah, I'm better at speaking. Better and worse at the same time.
Interesting.
Yeah, it's fun. Stable and getting on.
I know those people in there. All right. That was really fun.
I guess
Okay, we're walking through the park. Whew. All right.
Where do we go? This way, right? That way.
Sorry, it's right in the middle.
Can we go this way?
Yeah, go right ahead. There we go. Spins an amateur storm runner away from her. Yeah, well, Spin, you fortunately had to go through the hurricane, the recent hurricane. Here, I'm gonna actually do it. Yeah. I should just leave it. Okay, we're gonna do the sign off with our you know who it is. There he is. Here we go. Bright light. Ooh. Okay, still waiting to get in the shot. All right, everybody. I think we're in frame here. My service is a little wonky. But this was an awesome event. I'd highly recommend you checking it out if you're in the area, anywhere, even a few hours away from Brownsville. This is a really, really fun event. There's activities inside of the park building for kids, and there's activities outside. They have telescopes that you can look through. Obviously, this is my brother from another mother. I don't know what his name is, but super cute. And yeah, lots of very knowledgeable individuals and just a really great atmosphere. So it was 8 to 11 p.m. Central Daylight Time here at Resaca de la Palma State Park in Brownsville, Texas. And it cost $4. So you can't beat that. There's the Observatory you can go into and ask all the questions that you want. There's parking here on site. And yeah, it was really fun. So shout out to Victor, who runs the S.T.A.R Society, which is the South Texas Astronomical Society, on social media at S.T.A.R Society RGV. Thanks for putting on such a great event. This was awesome, and I look forward to attending another one soon. And thanks everybody for hanging out. Thank you anybody that asked questions, and shout out to my moderators. Whew, my legs are sore. My channel members and Patreon supporters, and anybody that sent over donations on PayPal, Cash App, or Venmo. Thank you so much. Jessica Kirsh here, coming to you live from Resaca de la Palma State Park. And that's a wrap. See you on the next stream, everybody. Love ya. See you soon. Thanks. And Nick, if you could end this for me, that would be great. Thank you very much. Good night, Mr. Man. See you next time. Be good. Bye, everybody. Mwah. See you.